Okay, so welcome everybody to 1 week more here at the demonstrations of Frenetic. Today in the menu, we have the Planar magnetic demonstration of Frenetic AI. But as always, we would like to start just giving you some introduction about what is our company. So just in a couple of minutes, we will review what is a Frenetic simulator, some intro about what is the main purpose of the Frenetic AI, and finally the magnetic planar demonstration. Before moving to that, I would like to ask Emmy, because in the last 2 weeks we have had a lot of people using our technology and as a demo testers and beta testers, giving us a lot of feedback. So thank you very much for all your feedback. We are considering all that part. And Emmy, do you want to give us some numbers or dates? You're muted.
Sorry. This I would like to thank you personally because these 2 weeks that we have already launched this our new product, we have raised more than 100 users. Many of you have downloaded the LC Spice. There is one winner that many of you has downloaded the flyback model for the LC Spice, following by the full bridge LLC. So it's great. And also the use of the suggestion design. And something that I really value is all these people that were connected, were engaging, sharing our feedback and by our forms or inside the platform. And I see that there are some of them in the meeting, so really grateful for this. And many of the changes that you have already proposed are things that we already have changed in our platform. So we take the feedback very seriously. We would like to grow together. We would like to build something bigger. So if you want to be part of something bigger, please keep sharing all the feedback. We will build this together and make some great things here. Thank you a lot.
Okay, thank you, Emmy. So let's come back to the slides. Okay, here. So first thing is you will see later that the main product at Frenetic is our Frenetic Simulator. It's an online software for designing and simulating magnetics, but from a power electronic perspective. So always you can start with power topology. We generate automatically all the waveforms and all the information needed to run the simulation, or also you can start from your own designs just to simulate. So some of the use cases that some of the users and customers have shared with us are here described, some of them. We just had a meeting with one PhD student in University of Miami, and he was explaining to us that since he had very few options of in the lab for building samples, he couldn't use the algorithm for suggest design, but he used Frenetic for verification and for loss simulation, and that was very useful for him. So that could be similar to the case, case 2 here. Other examples of use cases could be the design of a specific transformers where we have a lot of, let's say, complexity in finding this trade-off between the leakage inductance and series inductance, or having one or two components. That's a very particular case, very interesting. Also, when you have extreme conditions, like the number 6, where you have very high temperatures, high isolation voltages in industries like oil and gas, so it's very common. And the other thing is when you need to work with low frequency materials like nanocrystalline or amorphous material, also is a very typical use case. If you want to get a demo for free, don't worry. We are going to spend at least 1 hour with you learning from your needs and also trying to show you what we are doing. Here you have the QR code to request a demo, or just go to our website. Today, we are going to talk about the magnetic, let's say the planar magnetic generation, but also we will review all the Frenetic AI capabilities. The main goal for Frenetic AI is not to be one place to go and ask for things and don't come back in weeks. It's more a companion. So it's a technology that will allow you to take calculations that you are doing in your day-to-day. I mean, if you're simulating different circuits, or you are doing calculation for inductance, or you are doing analysis of topologies, this could be your companion, and having open keep the engineering in the loop and using the technology as a companion. So this is the typical process of designing a power supply. So we have some review of the electrical specs, then you have to choose a topology that maybe you have chosen from previous works, or even sometimes you define your specs to make the design using the topology that you already have. After that, it's very common to work with, let's say, create a circuit design, look for the components, customize magnetics, and build the hardware samples to finally get the hardware test. So here, everything that is in the kind of design and simulation part, I mean, from the first point and to the custom managed design and simulation, can be completed with this technology. So for the demo today, you will see how with just some single, very easy inputs, we are able to get the design of a planar. So let's go for the demo. Okay. So let's start for a flyback. Simple flyback of 40 watts with 50 volts input and 20 volts output, 40 watts. So we are going to choose flyback. Remember that you can always add all the information you need here in this box, like magnetizing inductance, switching frequency, anything you want to filter. So I'm going to confirm the input data. And I was playing with these before. So in your case, when you play with these, you will need to be more patient because it takes a couple of minutes. But this is the first solution of the system. So what I'm going to do is to run the planar. It's going to take some time. So I'm going to jump directly, wait for that is running. And I'm going to show you that first, once you have the design, also you can create the LT-SPICE circuit. So I'm going to, let's say, download the circuit, unzip. We have the download. Then I open the simulation file of this flyback that we just created. Everything is automatic, so I just download. I can run the simulation, and we can see this is also pre-configure the type of outputs we can see. The output is 20 volts, as I expected. And here we can see the waveframes in the transformer, in the diodes, in the voltage here. So you can do this for any kind of topology or any kind of configuration. So once you have that, you can ask for a design of magnetic, just not a planar, but design of a typical magnetic. So also just to go fast, I did it before. So here we have the design. So this is the design automatically created by this tool. And then I can type here my account at Frenetic. And if I come to my account of Frenetic, I can see how this new design appears here. So I can go to play with all the details of this design, checking, doing changes in the winding, in the core, or whatever. Here you will start seeing already nanocrystalline and amorphous are already included. And the most interesting part is that you can start adding more operating points to this simulation and see how this affects to the magnetic. Like, okay, you can have 50 volts, then in the second point you have 70 volts. You can run the simulation and verify if the system works in this report, like, okay, for both cases are different results, so you can check that. And finally, let's see how the Planar, so how the Planar is going, is loaded or is loaded. Okay. Okay, we have already here the results. So for this case, what we have is a E22, material 3C97, and just one gap in the center leg. We have 8 turns in primary and 4 turns in secondary. It used 2 layers in both cases. The total number of layers is 4 with, let's say, I think you will see the ons, or I think it's few ons. Here you cannot see, but in the detail, we have also calculated the current density and all the parameters needed. This is the magnetizing inductance. This is the leakage inductance between primary and secondary, and that are the losses. So this is the core losses and the winding losses, and the total losses 1.1 watt. So it takes like 2 minutes to get these calculations. So now let's move to the second example. Let me move to here. So the second example is going to be a full bridge. So I'm going to start with a 200 volts, 150 volts, and 600 watt. I'm going to choose full bridge and repeat the same operation. So this is ricochet, so it's really fast, but for you, it will take like 1 or 2 minutes. Now I'm going to ask for the suggest of the Planar. It's going to start doing the calculations, and I'm going to jump to the next tab to go faster. So here, what I did is to request the download the file. So again, I can download the LTSpice file. Opening. Open, yeah, right here. Yeah. So I can come here. Sorry, this is the one that I need to choose. Let's go. Now we have a full bridge. So you can see the full bridge with all the specs. And now here is the output of the simulation, where we can see the waveforms of the gate signals, the transformer, the currents, the output, and everything. So you can download even these files to run more specific simulations. And once we have that, we can ask for the design of a classic magnetic. In this case, could be this transformer and this inductor. So this is the design of the transformer, main transformer, and the output inductor. So we already have this. We can see the dimensions, total losses, 5 watts here and 1.9 watts here, temperature. And if we want to check the details, again, you can come back to open Frenetic simulator if you have an account. Let's see how the evolution of the Planar thing. So here we have an error. Let's run again, and it will take some time. As you can see, this is not, this is a real demo, so sometimes we can have some problems. Just in case of that, I preload some of the cases. So it's here a few minutes ago. So for this full bridge phase shift of 600 watt, we generated this case on ER51 3C95. We have 8 turns in primary and 8 turns in secondary, and these are the total losses 6 watts. We can see that the way that we present this is 1.2 millihenries, but is a very nice way of representing this. And the interesting thing that I want to show you what is happening in the back is that we have using a technology that allows us to do calculations of the winding losses in more detail. So for example, for the core losses, we use the same engine that we use for Frenetic simulator. So it's like the evolution of the statement. And for the winding losses, we are actually doing a kind of simulation with the harmonics. So what is happening in the back is something like this. So we are reloading all the configuration of the Planar PCB. We check all the waveforms and we check all the harmonics that we are interested. So we can check up to 10 harmonics. And we use that to compute all the losses that are using, let's say, also finite domain analysis technology to verify what are the losses. So also here we can see the inductance, the metrics of inductance, and for all our pay customers also they can have access to these details in case that they are interested. Let me start sharing to see that I think we have a lot of questions. So this is the end, let's say, of the demonstration of how this planar can be generated just with the simple inputs. Before moving to the questions, I would like to remember you that now every next week we will have another demonstration. We will focus next week in an LLC design together with the transformer. The idea will be to show you how taking some inputs for a specific LLC, how we can play with the design of the parameters and then create the transformer. We're going to analyze which option is better to have a planar or a concentric. So here you have the QR code, and also you will receive an email to receive that. I invite you to use the QR code for the registration. And yeah, now let's move to Q&A.
Thank you, Gemma. Yes, we have a couple of questions. One of the questions is regarding if the tool for Planar is calculating the capacitance too.
Yeah, that's a good question. So what we are doing with the FEM, actually, that we are calculating the leakage inductance, and now we are also calculating the capacitance. It's not so here because what we are is verifying in the lab the results. Our modeling team is obtaining very good results, so we expect to include the parasitic capacitance in a matter of weeks or maybe a month. I don't know exactly, but it's something that is going to be in the short term included. It's actually following the same structure that we use for the leakage inductance.
Okay, great. And also we have an additional question of Sam. If the AI routing turns, we are routing the turns of the PCB with AI, this is a common question.
Yeah, it's a great question. So this is our plan for the future, but it's not happening right now. But our vision for the future is that we will be able to create all the files to be connected directly with the PCB supplier. So once you have, let's say, the inputs, we generate everything, we are doing verifications, and we end up creating all the files that a PCB supplier will need. And even we can connect with one of those PCB suppliers. So the answer right now is in work in progress, but this is our vision, to being able to connect directly with the PCB supplier.
Yes, great. And well, an additional question of Sharpie that, the half-bridge LLC also is something that we have in mind in the near future. So we would like to offer a wide range of topologies so you can cover all the cases. We have already one developed, and now some others are on the way to be developed. And I think that there is one more question of Mark regarding the wire sizings.
Yeah, I mean, thank you for your question, Mark. So the point with the sizes is basically right now, the only limitation is the library of cores for planners. So I think that right now we are using the library, one of the libraries from Ferroscube and TDK, but this is something that in the future could be very easy modified. So right now, this is the limitation that we have put for the beginning, but the idea is that there is no limitation for that. the main limitation is that this version of Planar is using PCB. So our natural evolution will be to do planars with other type of foils and other type of technology that allows us to increase the current and then create much bigger planar magnetics. But yeah, that's let's say that's the direction. There are not going to be kind of limitations in that size the future.
Okay, great. And just to remember, we are sending the credentials so you can access to our tool, the one that Chema demonstrate. As we mentioned, this feature regarding the planners is not yet in the application. You will receive a notification when this is available for you. But remember that you have the opportunity to suggest a design and download your LT Spice model, and also the other feature to, according to your topology, to get a design. So you're getting all the credentials. And additionally, we have extended this trial version for all the people for this event. So take the note for the next event and the ways to extend this trial.
Exactly. And something I would like to comment here is about there is a last question about if we will connect with magnetic manufacturers too. So the goal, I mean, we are not going to manufacture these PCBs or any of those magnetics, but we have a bunch of partners that are users of our technology that they are manufacturers that will take place. But for the planners, our goal would be to find a couple of suppliers that could be internationally used and then can be connected, but always you can use your own supplier. So you can download all the information. So we won't force anyone to work with any supplier, but of course, always we will offer our partnership connections to all the users of Frenetic AI. So this is a question here from Basin. I'm not sure if I understanding the whole detail, but it's saying that in your design, if we integrate the resonant inductor, so something I mentioned before, and I think that it's going to be worth it to share my screen again, is that let me share my screen, and we take this as the last question. Sorry, I don't find where is the call. Okay, here. Okay, so the integration of the leakage inductance in the resonant parts. So when you are designing a transformer, let's say resonant transformer, like LLC, for example, one of the questions that you will need to do to check, and this is something also that Frenetic AI can help you, is that if you want the inductor to be integrated or not. If you decide yes, the design is going to try to suggest you a leaky inductant that is going to be exactly the same value that the one that you put as a resonant. And if it's not possible, then it would tell you, I cannot do it, and then you have to move to a no integrated inductor. But this is also part of the game. So if you, for example, try to make an inductor and it's not possible, you can always play with that numbers. And also that's the good thing about Frenetic AI with the design of the topology, that you can come here and make an analysis for different cases. Even you can write a range, and then the system will play with the range and create the tables where you can see which one can be more, let's say, interesting for you, and see how to play with the magnetizing, output, resonant, or whatever. So I think that we are already out of time. So thank you very much for coming today. And yeah, I don't know, Emmy, Ellie, you want to say something?
Yes, thank you a lot for your time here now and to testing our tool. We expect for you next week and keep using our tool.
Yeah, we'll see. We send you the invitation for the next webinar, of course, for next week.
Okay.
Thank
See
you.
you.
Have
Have
a
a
nice
nice
week.
day.
Bye
Bye bye.
bye.